Swayam Prabha. Digital India. Educated India.
We have so far seen different forms of corrosion and also different ways in which we can protect metals from getting corroded. And now we will come to methodologies for calculation of the rate of corrosion, so that we know as to what is the rate at which we are going to lose material from the structure. So now here it is just to revise what we had done earlier, and the concept of half cell is going to come into picture, and we have two types of electrode potentials. One is an equilibrium electrode potential, in which the reduction and oxidation reactions are equal, and therefore there is no net reaction taking place. So the rate at which oxidation takes place and the rate at which reduction takes place, both are the same, and therefore the cell is at equilibrium with regard to reduction and oxidation. Now when it comes to a reference electrode like hydrogen gas, you have a platinum electrode over here. It is a noble metal, and this serves as a surface to facilitate oxidation or reduction of hydrogen. So platinum per se does not react with anything, but platinum just provides a surface area for this hydrogen to either get oxidized or reduced. So we have this half cell, and we have also seen how the oxidation and reduction takes place at these two electrodes. Now here what we get is an equilibrium potential. So what we get is at an equilibrium potential, and when it is compared with hydrogen, let us say this half cell is paired with a hydrogen electrode here, then the kind of potential we will get has been listed over here. So we have a reference electrode in hydrogen electrode, and we find electrode potential with reference to the hydrogen electrode. So that is the idea in all our discussions. Now polarization is the displacement of each electrode potential from its equilibrium value. So what it means is that when equilibrium is lost, okay, when the equilibrium is no longer present and the material is corroding, so you have a net reaction taking place. The net reaction is that of, let us say, metal going into the solution as 2 plus ions, and then electrons going from the metal, that is anode, to the cathode. So this platinum together with hydrogen, so basically it is a hydrogen electrode acts as a cathode, and then the electrons go from here to there, and then the hydrogen ions get reduced to hydrogen gas, whereas here zinc is getting oxidized to zinc 2 plus ions. So now here you have a situation where oxidation and reduction are not in equilibrium, because at this particular electrode, unlike the previous case, the zinc going into ions and zinc coming back are not in equilibrium. Therefore there is a net reaction between zinc and this electrode, so that zinc is being lost continuously, zinc is being corroded out from here. So that is the reason why we call this difference between the voltage generated here during corrosion from the equilibrium voltage where there is no net reaction, as polarization. So, polarization is a particular term which is applied to the deviation of the situation, the deviation of the potential, electrode potential from its equilibrium value. So, when the electrode is corroding, then it will deviate either towards the negative side or positive side of the equilibrium potential. So, let us assume that for this particular situation where it is a non-equilibrium condition, the electrode has a potential of minus 0.621 volts and the equilibrium potential is 0.763 volt with respect to hydrogen. So, here also the non-equilibrium potential is essentially minus 0.621, which is different from the equilibrium potential of 0.763 volts. So, this so called over voltage which is indicated by eta is equal to minus 0.621 volts. So, this is basically the potential of the non-equilibrium condition minus the potential of equilibrium condition, that being the reference, and so this over voltage is in the range of 0.142 volts. So, the displacement of the electrode potential from its equilibrium value is to the extent of 0.142 volts, and what you have is rate of reduction and rate of oxidation are identical at equilibrium, and that is precisely what is absent in this case. So, naturally you have a slight difference between the rate of reduction and rate of oxidation. So, oxidation is might be moving faster, so that the corrosion takes place over here, and so you get this kind of additional voltage. Now, the condition in which the reaction rate is controlled by the step in series that occurs at the slowest rate is called as activation polarization. So, here for example, adsorption of hydrogen ions on the surface is on the zinc surface. So, when we talk about zinc here, it is hydrogen ions are getting adsorbed onto the zinc surface. Then electron transfer from zinc to form a hydrogen atom. So, you have zinc ion hydrogen ion getting adsorbed and an electron coming over here to form a hydrogen atom. So, now hydrogen is reduced to H. Okay. So, hydrogen is reduced to H by virtue of electron joining the H plus ion over here, and then two hydrogen atoms combine to form a diatomic hydrogen gas which gets liberated, and many hydrogen molecules, that is diatomic molecules, will combine together to form a bubble something like this. So, that is what happens in case of what is called as activation polarization, and the slowest of these four steps determines the rate of overall reaction. So, the condition in which the reaction is controlled by the step is in the series that occurs at the slowest rate, and an activation energy barrier has to be crossed. So, this activation energy barrier is associated with the slowest rate or the rate limiting step. So, now we see that electrons are being generated at some other point by virtue of oxidation of zinc. So, in fact, in the previous classes we had seen that at even if zinc is a single piece, at some point you have oxidation where maybe the stresses are high or where the residual stresses are present, the grain size is different. So, there are various reasons why there can be cathode and anode created within the same piece of metal, and there is no way we can separate them out or isolate them. So, here you have electrons coming from the anodic region of the same metal, and these electrons then combine with these hydrogen ions. Now, this reaction and the other reaction, both reactions have to be balanced, because if the rate at which one is moving will generate electrons at that particular rate, and they have to be consumed here by hydrogen ions at the same rate. So, that everything remains in equilibrium. Now, what we need to see is that among these 4 steps, which one controls the rate of the reaction. So, depending upon what which process is the slowest, adsorption or maybe combination or coalescence. So, what is the one that results in or which slows down the reaction. Let us say which of the steps is the slowest, say adsorption could be the slowest process, in which case the activation energy for adsorption will govern the rate of reaction here. So, rate of reaction in the other part of the electrode and rate of reaction in this this part of the electrode, meaning rate of reaction in the anode and rate of reaction in the cathode has to be equal, so that the electrons generated at the anode get consumed at the cathode. So, overvoltage and activation polarization is given by beta log I by I naught. So, I is the current density here. So, the current density in non-equilibrium condition, I naught is the current density essentially in exchange current density, which is in equilibrium condition. So, basically what we are trying to see is that when there is no net reaction in equilibrium condition, when the oxidation and reaction reduction reactions are proceeding at an equal rate. So, at a given electrode there is neither reduction nor oxidation. So, this kind of exchange current density or this kind of current density is seen as the reference exchange current density. I is the current density under non-equilibrium condition. So, this is the non-equilibrium condition which is being portrayed over here, and so the corresponding over voltage is proportional to the so beta is a constant and it is proportional to logarithm of I divided by I naught. So, this is the over voltage for activation polarization. So, here you need you need activation energy barrier to be crossed for of one of these events to take place, and higher is the activation energy, slower will be that event, and therefore, that will govern the rate of reaction. So, what we are saying is that we can equate this rate of reduction to rate of oxidation and to the current density at equilibrium, and so find out I naught as the exchange current density. So, and then we plot current density versus over voltage. Now, here this line indicates the relationship during reduction of hydrogen. So, this is basically the anode this is basically the cathodic region, this is the anodic region where the hydrogen is getting oxidized, and the two lines meet where the two are equal. So, here what we see is that the reduction reaction is more, here the oxidation reaction is more, and they get balanced exactly at 0 over voltage. So, this is the equilibrium situation as which is portrayed over here, and so we get the I naught corresponding to H2 to H plus and back. So, the H2 and H plus are at equilibrium and there is no net reaction taking place over here. So, whenever there is no over voltage, then it means that there is no net reaction taking place. So, the deviation can be either due to an anodic reaction where the over voltage increases and so does the current density. So, over voltage and current density both increase hand in hand, whereas in case of the cathodic reaction, the current density continues to decrease. The current density starts with a relatively higher current density, it continues to decrease up to a point where equilibrium is reached. So, so these are the two trends which are seen at anode and cathode. Another variety of polarization is called as concentration polarization, where the diffusion of these ions through the electrolyte is taken to govern the rate of reaction. So, when the reaction rate is low, when the reaction rate is low. So, which reaction rate is low? The reaction of electrons combining with hydrogen generating hydrogen gas, for example, and so when the reaction rate is low, you get fewer electrons, from the anode, and since you are getting fewer electrons from the anode in a given period of time, the rate of reaction at this point is also relatively sluggish, and that is why there is always an adequate supply of hydrogen ions in the solution near the electrodes interface. So, if concentration of H plus is high for some reason, say you have deliberately added some mixed chemicals which will give a large concentration of H plus ions, or fewer electrons, very few electrons are being generated, meaning the anodic corrosion is so slow, anodic corrosion is happening so slow that very few electrons are generated, and they are not enough to combine with all so many ions. So, then there is a increase in concentration, and so there is a concentration polarization taking place at high rates or low H plus concentrations. So, where you see that the rate of reaction is very high. So, plenty of electrons are available, they come here and then they rapidly combine with H plus ions to give out gas. Okay. So, there you are you have a serious shortage of H plus ions, because they get depleted very rapidly, right. So, this is a depletion zone. So, this region is the depletion zone where the H plus ions and electrons are combining very rapidly, resulting in H, and then that H combining to H2 as a diatomic gas, and then finally that diatomic gas forming bubbles. So, this depletion zone is the region where H plus ions are in short supply. So, the interface is not able to replenish the the interface is not able to consume the excess electrons which have been arriving here, and so the replenishment of hydrogen ions is not as fast as it should be. So, the reaction is faster than the replenishment of the hydrogen ions. So, concentration polarization exists when the reaction rate is limited by diffusion in the solution. So, the reaction rate is governed by the diffusion in the solution. So, there you had the activation energy of adsorption, whereas here you have activation energy of diffusion that will govern the concentration polarization. So, activation polarization will be governed by the activation energy of adsorption, whereas here it will be governed by the activation energy of diffusion. So, if we are able to get this to diffuse faster, then the reaction here also can get speeded up. So, diffusion of H plus to the interface is rate controlling, and the system is said to be concentration polarized. So, the concentration here can be either high or low depending on the rate of diffusion there. Now, in case of concentration polarization, the over voltage is independent of current density until a certain limiting current, and then that over voltage drops very rapidly. So, so that is what happens. So, it's similar to what is called as breakdown type of situation. So, you have for large current densities, the over voltage is same, and at this point the over voltage decreases abruptly. So, the very abruptly in magnitude, right here, and this over voltage is calculated based on this formula 2.3 RT upon N Faraday's constant log of 1 minus the current density in a given condition divided by IL, right. And generally speaking, concentration polarization is not the rate controlling process for oxidation reactions. So, oxidation reactions, concentration polarization is not the rate. So, mostly reduction reactions are the ones where concentration polarization is significant. Normally what we find is a combination of concentration and activation polarization. So, here you have this activation polarization, and then part of the region you have concentration polarization. So, what it means is that up to the point where the over voltage drops steeply, the over voltage is not constant, but it decreases from a specific value at low current density up to a point and then drops very rapidly. So, this is a combination of concentration and activation polarization. So, now what is the significance when it comes to corrosion? When it comes to corrosion, basically we are talking about rates of reaction. So, if we control the rates of reaction, so many of these inhibitors, they interfere with these rates of reactions and then prevent one reaction from taking place, so that the other reaction also tends to slow down. So, that is how the polarization or study of polarization will help in deciding how we either enhance the activation or reduce the activation. So, supposing you want to deposit a coating onto a surface, then you need the surface to be reactive. So, you want to activate the surface, right, because for coating to be deposited, you need to have a chemical reaction between the solution and the surface. On the other hand, if you want corrosion protection, then you do not want reaction of the corrosive environment with the surface, due to which you would make sure that these reactions are such that the rate of reactions is so slow that the corrosion or removal of material from the anode is minimized or completely prevented. So, it all depends upon our objective, whether it is to develop a coating or modify the nature of the surface for various reasons, like you do phosphating and so on. So, that is intentional reaction with the surface modification, chemical modification of the surface. However, when we talk about corrosion and corrosion protection, implicitly we mean that it has to be prevented. So, we need to prevent the reaction between the corrosive media and the interface or the surface of the material. So, this is the picture of activation and there are few parameters over here. So, now here you have different values of voltages. So, here you see that there is a voltage corresponding to equilibrium voltage, and due to activation polarization, the voltage and the current density both increase, and then there is a it intersects this curve of activation come concentration polarization of over here, and so this is the corrosion potential and this is the corrosion current density that is observed over here at this point of intersection. So, that is what we will see in some detail in the next slide. So, if you look at the polarization curves and relate them to corrosion rates. So, we will see how this electrochemical potential with respect to hydrogen can be linked with the different phenomena in corrosion, and therefore, we can predict the corrosion rate. So, upon immersion both hydrogen and zinc. So, now we are talking about corrosion of zinc, and the anode is zinc, cathode is hydrogen. So, both experience activation polarization along the respective lines. So, you have this line, let us say for zinc, activation polarization line for zinc. This is the equilibrium, this is the equilibrium condition. So, this is the equilibrium condition for zinc to zinc 2 plus, and the corresponding equilibrium current density is seen over here. Now, there is a deviation. Now the zinc is going into solution. So, there is an anodic reaction taking place at the anode, Zn2 plus giving 2E minus, and then there is a reduction at the cathode taking place, a reduction of hydrogen with 2H plus 2E minus giving the hydrogen gas. So, this then gives us the intersection of the two gives us the corrosion voltage and the current density of corrosion. Why? Because the rate at which the electrons are being generated and the rate at which electrons are being consumed matches at this point. And so, we have the electrode potential corresponding to Vc and Ic as the corrosion potential and the corrosion voltage, corrosion potential and corrosion current density, sorry. Yeah. Now, if we have to calculate the corrosion rate of zinc, then we use, instead of I, this value of Ic, because now this is the corrosion current density. So, this is the current density at the time when zinc is getting corroded. So, the rate of corrosion would mean that it is equal to Ic upon Nf. So, there is no net charge accumulation at any point, and so the oxidation and reduction reactions at this point are equal, and so corrosion proceeds under the condition that all electrons generated are consumed. So, there is no net accumulation of any kind of charge. So, let us take a numerical example where the zinc, again the same system, zinc and hydrogen, and the rates of oxidation and reactions, oxidation and reduction of the half reactions are controlled by activation polarization. So, we are not bringing in corrosion, we are not bringing in the concentration polarization yet, it is only activation polarization. And anyway, we have seen that concentration polarization is not the rate controlling mechanism or not the rate controlling step. So, now we have for zinc Zn2 plus, that is equilibrium potential minus 0.763 volts, and for hydrogen it is 0. I naught at equilibrium is 10 to the power minus 7 ampere per square centimeters. For hydrogen it is 10 to the power minus 10. Beta, the constant, is at 0.09 for zinc and minus 0.08 for hydrogen. So, this is the data that is given to us, which will enable us to locate this. So, this point gets located automatically. We have I naught and V naught there. So, now we see that for hydrogen we have VH. So, this is the equilibrium plus beta H log I by I naught. So, so this is the reaction at the cathode, which is a reduction reaction, and this is the equilibrium condition, and that is the deviation from equilibrium. And so, what we see here is that Vzn equal to Vzn plus beta Zn log I by I naught. So, what we are essentially looking at is this line. So, here we are looking at this line. So, we are going this way, and there we are coming back. So, I naught plus H2 is here. So, from here we come this way. So, and then by setting Vh equal to Vzn, because at this point of intersection the two become equal, and so we are able to get this expression. And so, we have beta zinc is known, the beta hydrogen is known, current, now the current density has to be calculated, but I naught for both these things are known. So, if you take the current density to be the IC, that is corrosion current density. So, let us see this. So, what we are calculating now is this, because now we came down this way, we went up that way, and at the point of intersection where VH and V zinc they both become equal, we have IC and VC. So, that is what we are trying to determine over here. So, so if we manipulate these two expressions, I mean the left hand side and right hand side of this expression, then we have log IC equal to 1 upon beta zinc minus beta hydrogen, VH minus V zinc minus beta H log I naught hydrogen plus beta zinc log I naught zinc. and putting the values in, what we get is minus 3.924. So, this is log IC, and so the corresponding value of IC is the current density of corrosion is 10 to the power minus 3.924, which translates to 1.19 into 10 to the power minus 4 ampere per square centimeter. Now, the rate of reaction is given by IC, that is the corrosion current divided by N into Faraday's constant. So, N is equal to 2 because there are 2 valence electrons which are being given away by zinc. So, you have N is 2. So, IC is the corrosion current which we just calculated, and that is 1.19 10 to the power minus 4 amperes per okay. So, this is they have put ampere as coulomb per second, that is why the coulomb comes in here, and that is to balance the unit. So, just to show that the Faraday's constant coulomb per mole. So, instead of saying amperes per square centimeter, they have said it as coulomb per second. So, both are same, but then to show the units, I mean to put things in coulomb, centimeter and seconds, they have used the definition of ampere as coulomb per second. So, this expression therefore works out to 6 point. So, rate of the reaction is rate of reaction at this particular corrosion current is 6.17 into 10 to the power minus 10 moles per centimeter square in second. So, per centimeter per second effectively. So, this is basically the rate of corrosion 6.17 into 10 to the power minus 10 moles per centimeter square area per second time, right. So, what it means is that supposing you have piece of 1 square centimeter area, let us say you have iron being now here it is zinc of course. So, here it is zinc, and you have a 1 square centimeter area of zinc. Now, zinc molar weight, weight of 1 mole of zinc is let us say some value x. So, now here the actual amount that is being lost is 6.17 into 10 to the power minus 10 into the molecular weight of zinc. So, it is an extremely small amount, but this is per centimeter square per second. So, per minute, per hour, per year, it will get multiplied by appropriate values, and accordingly the rate of corrosion at the end of a certain period of time or the total corrosion over a period of time can be calculated. So, here the rate is given, but then one can calculate the overall corrosion, overall amount of loss of metal per year per unit area for the or for the entire area of the component. The corresponding voltage, corrosion voltage is given by this expression, beta h is minus 0.08 volts log of IC by I naught hydrogen, and so the Vc is minus 0.486 volts. So, that is what is shown over here. So, Vc is minus 0.486 volts. So, that is seen in the in this particular graph. Now, we come to passivation. So, let us talk about passivation, and contrary to activation, the material becomes passive in the sense it no longer reacts. So, here what we were talking about is anodic reaction, material prone to reaction, dissolution into the corrosive solution, but when in context of passivation we do not get any kind of loss of metal. So, some normally active metals and alloys lose their chemical reactivity and become extremely inert, and this is called as passivity. Passive behavior results from the formation of highly adherent and very thin oxide film on the metal surface, which serves as a protective barrier to further corrosion. So, even if that film is removed, by some means a new film forms immediately. So, because of very high affinity of the base metal and presence of sufficient quantity of this material like chromium for example, the chromium oxide gets formed almost instantaneously and therefore protects stainless steel from oxidation. Well, stainless steel is not all that stainless in the sense that in the presence of chloride ions for example, it does get corroded. So, this chromium oxide is a film that does not withstand the onslaught of chloride ions, but for most of the conditions, most of the aggressive conditions, this stainless steel is able to withstand these conditions and hence is used for many applications including appliances, including hospitals, including surgical applications and a big many applications where you do not have any contact with the or you do not have rusting due to these chlorine ions. It is a common experience that a stainless steel spoon left in a bottle of pickle corrodes very rapidly. So, we will see that if you have left a stainless steel spoon in a bottle of pickle for a sufficiently long period of time, maybe a few months or so, you will find that it has got corroded at various locations, and that is because of the chloride ions which is a weakness as far as stainless steel goes. Now, aluminum is highly corrosion resistant in many environments because it also passivates and it has a tenacious oxide film that is present there which prevents any contact with the environment, with the corrosive environment. And if the film is damaged, the protective film again reforms immediately. So, if you try to remove this protective film from the surface, it forms almost immediately. So, if you try to let us say abrasively remove it or grind it off, it will form immediately. However, if the environment of the or the corrosive environment changes, okay, the nature of the environment changes, the concentration changes, then the passive surface may become active. So, this is one thing which we need to remember in mind. So, here what we see is a very familiar curve up to this point. So, here you have oxidation, here you have reduction, and these two are at equilibrium. So, on this axis we have electrochemical potential, not over voltage, it is electrochemical potential. And as the oxidation takes place and the current density increases, beyond a certain current density, the current density starts decreasing and the oxidation potential remains practically constant. So, current density moves backwards, oxidation potential or the electrochemical potential practically remains constant. Here there is a very mild or marginal rise, but then it practically remains constant, and then in this state even if the potential continues to increase, the current density is very low, and so this is the passive state of the metal. But then it can become transpassive, that is it can again start going up as the current density increases. The potential can go up with increase in current density. Now, here for example, we have a situation where you have a reduction reaction taking place at the cathode, and you have two different solutions which lead to the reduction, and at the cathode you have two different species of atoms. For example, in one case you may have hydrogen, in other case you may have something else. Now, here if you see, now this is the line corresponding to the anode, okay, this is the line corresponding to the anode, and then you have the reaction with the cathode. So, in this case the metal M will undergo a higher corrosion rate in solution 1, that is because IC, the corrosion current which intersects this line, is much higher than the corrosion rate of the second solution. For example, ICB is much lower, and so the rate of corrosion is much smaller here as compared to the rate over here. So, this is what we mean by the reduction polarization lines for two solutions for let us say an electrolyte or a corrosive medium intersecting with this line. So, whenever you have an anodic reaction taking place over here, since the electrochemical potential and the current density increase hand in hand, the corrosion rate is higher, whereas in this case where the reduction polarization line shows that the polarization is reduction polarization is taking place at higher electrode potential and the current density is increasing, electrode potential is decreasing as shown here, then because of this high electrochemical potential, the intersection occurs in the region of passivation. So, here you have a much smaller current that is established, due to which the corrosion reaction is extremely small, and therefore, it's extremely unlikely to get corroded fast. Now, here itself, when we did the solution to that problem, we are talking about a corrosion rate of say 10 to the power minus 10 moles per cc, right, per square centimeter, sorry, per square centimeter. And so, the anodic reaction itself is extremely slow. It is not that it is going to just get dissolved within minutes, but it is very slow. And if this current density reduces, now mind you that this current density and this current density are orders of magnitude apart, meaning that since this is a log of current density, this could be, let us say, 3 orders of magnitude, let us say 1000 times less. So, this current density ICB would be about 1000 times less than current density at A, and that is the reason why it makes so much of a difference when it comes to the rate of corrosion. So, if we calculate the corrosion rate with this, we might get it 3 orders of magnitude less than what happens here. So, that is how the passivation results in again further increase in corrosion resistance. On the other hand, if let us say one electrolyte is here, now that there is a change in the nature of electrolyte, or there is a change in the corrosive environment, then you have a new corrosive environment which is something like this, then the passive surface, now here the surface would behave passive because the current density is so small, and this polarization line intersects in the passive region, in the passive region of the metallic surface. But then the corrosion medium changes, the environment changes, and then you get a different line here. So, now this intersects in the active region. So, here now the material is going to behave in an active manner, because now the medium has changed, and so its reduction polarization line is now something like this, and so the current density would increase from ICB to ICA, and then the corrosion will proceed relatively faster. So, this is what is important when it comes to corrosion and prevention of corrosion. So, what we have seen, to summarize, is that there are various ways of preventing corrosion. Either we interfere with the with these reactions. So, we interfere with the reactions at anode and cathode, especially at the reaction in the cathodic region, and we also render the material passive by having a film of material that is deposited, so that the so even if there is corrosive media, still the over potential is relatively high, and the intersection of the polarization line takes place in the passive region, so that you get extremely small rate of corrosion. So, we stop corrosion or we prevent corrosion by applying by passivating the surface, by generating kind of oxide which will prevent the material from any further reaction with the environment. So, we have seen a number of corrosion protection means. So, you have a very brute force method where you connect a negative terminal of a power source to the material to be protected from corrosion. So, this is particularly true with big structures where you might not be able to use other methods of corrosion which we discussed earlier, like painting for example, or inhibitors or protective coatings and so on, because that will require enormous amount of surface to be coated in a very uniform manner. Plus you would like to not indulge in maintenance of these structures too frequently, and therefore it is important to therefore connect these negative terminal here and make it into a cathode and protect it. So, we have seen different types of corrosion and corrosion protection methods, and it is possible to minimize the degradation, although it might not be possible to completely avoid that degradation. Okay, now we need to calculate the rates of corrosion, and whenever we immerse a metal in a corrosive medium, the corrosion does not take place according to the equilibrium type of situation. Usually there is polarization taking place, and therefore there is always an over voltage getting generated. So, the rate of corrosion is governed by the reaction of the metal with the corrosive medium. Now, in the present example, what we see is that zinc experiences corrosion in an acid solution according to this reaction, where zinc gets oxidized to zinc 2 plus, and the hydrogen ions get reduced to atomic hydrogen, diatomic hydrogen gas. Initially it gets reduced to atomic hydrogen, and then that atomic hydrogen gets combined to diatomic gas H2, and then here the both oxidation and reduction rates are governed by activation polarization. So, basically we will have to calculate the rate of oxidation of zinc, and therefore the loss of amount of material that is lost from the zinc plate. So, we have some data that has been given over here, and the solution proceeds as follows. So, we have this equation given as Vh equal to this is the equilibrium part plus beta H log I by I naught. So, I naught is the exchange current density. So, this is an equilibrium type of situation, and beta is a constant which has been assigned as the value of minus 0.08. And so, for the zinc oxidation, similarly we have this equation, and if we set Vh equal to Vzn, because unless these two are equal, the matching between the two reactions will not take place, meaning that all electrons which are generated during oxidation have to be consumed in the reduction reaction. So, that condition is met only when this equation is satisfied, Vh equal to Vzn. So, this is equated with that, and what we are interested in finding out is the current IC, that is the corrosion current, so that when we use the IC in this rate formula, we can get the rate of corrosion of zinc in moles per square centimeter. So, moles per square centimeter per second actually, yeah. So, that is the rate of corrosion. So, in order to calculate the corrosion rate, we need to find the value of the IC, that is the corrosion current. So, if one solves this equation for IC, so this basically is going to be IC, right, and so here you have one single value of corrosion current, because we have seen in the previous curves, like here for instance you have this is the oxidation line. So, I naught is over here, and then there is an increase in the current density up to a certain point where V corrosion is reached, and this is the value we are trying to find out, because this is a line of oxidation of zinc, this is a line pertaining to reduction of zinc, and where the two meet we get these 2 points Vc and Ic. So, we need to therefore calculate the value of Ic, and so you get the value of Ic using this expression to be minus 3.924, and that is a value of log Ic, and the corresponding value of Ic itself is so much, and the corresponding value of Vc is turns out to be minus 0.486 volts, because this equilibrium voltage is 0 because it is hydrogen, and BH is given as minus 0.08, and then the corresponding value of Ic and I naught are put here, and you get minus 0.486 volts as the Vc. Now, if you look at the first problem, we see here that the corrosion rate of zinc is equal to so much as we have just calculated. Now, what we need to find out is what is the corrosion penetration rate. So, I know that certain number of moles are going to be lost per square centimeter per second, but then we need to find out the corrosion penetration rate in 1 year for an area of 100 square centimeter. Okay. So, we have so many so this corrosion rate is per square centimeter per second. The CPR, the corrosion penetration rate, is given as Kw upon rho A T. So, K is the constant, W is the weight of the number of moles which are lost. So, the rate of corrosion is expressed in terms of say milligrams per unit time and per unit area. So, rho is the density, A is the area, and T is the time. So, the units are very important. If we need CPR, corrosion penetration rate in mils per year, that is in terms of inches, then so mils per year is milli inches per year, and the corresponding value of K is 534. So, the amount of material that is being lost has to be in milligrams, the density should be in gram per cc, area should be in square inch, and time should be in hour. So, what we do is that the corrosion rate per hour is given as 3600 moles per square centimeter second, and that is 2.2212 into 10 to the power minus 6 moles per square centimeter hour. Now, 1 mole of zinc is 65.38 grams, and therefore, we convert this into actual weight of zinc that is lost per hour. So, the weight lost in corrosion is equal to 2.2212 into 10 to the power minus 6 into 65.38. So, this is the corrosion rate per hour, right. So, this is the corrosion rate per in moles per square centimeter per hour, and this is the atomic weight, meaning weight of 1 mole of zinc. So, this gives us in terms of grams. So many grams per square centimeter per hour. So, this is 0.142206 milligrams per square centimeter hour. Now, the density of zinc being 7.133 and K, since we want to get the value in millimeters per year, is 87.6. So, the CPR in millimeter per year is 87.6 into so much, and so that makes it 0.0178 millimeter per year. So, we need to be watchful about the units of the various quantities as given in the adjoining table. Typically, half a millimeter per year is acceptable corrosion rate. So, this is much lower than that, and therefore, it is perfectly okay. So, instead of 0.5 this is 0.0178. So, which is almost one third of the corrosion rate of what is acceptable. Okay. The next problem pertains to one half of an electrochemical cell consisting of a pure nickel electrode in a solution of Ni2 plus ions. Okay. So, we are talking about an electrochemical cell with a pure nickel electrode with Ni2 plus ions. The other half is cadmium electrode immersed in a Cd2 plus solution. Now, if both are 1m solutions, then it is like a standard electrode, and then we compare V naught for Ni to Ni2 plus and V naught for Cd to Cd2 plus, and then we compare the spontaneous standard voltage that is generated. So, this becomes a standard cell, then the spontaneous overall reaction is going to result in a certain voltage that is generated based on the electrode potentials relative to hydrogen. But then if the concentration deviates from 1 molar concentration, for example, cell potential at 25 degrees centigrade, if C2 plus and Ni2 plus concentrations are 0.5, not 1 mole, but 0.5 and 10 to the power 3 minus 3 moles. So, cadmium is 0.5 mole and nickel 2 plus is 10 to the power minus 3 mole. So, now the question is the spontaneous reaction direction still the same for the standard cell? So, we need to find out whether the whether one gets what was getting oxidized earlier is getting continues to get oxidized or not. That is the question here, because when these concentrations change, then it is possible that what was an anode earlier can become a cathode, what was basically what was getting reduced earlier gets oxidized, and vice versa. So, let us see how it works out. So, the first part is fine, the cadmium electrode gets oxidized and nickel gets reduced, because in the EMF series, okay, cadmium is lower than nickel. So, cadmium is lower than nickel means nickel is more cathodic, lower means anodic. So, if anything is below in the EMF series, then it is more anodic. So, Cd is more anodic to nickel, right. So, Cd gets oxidized to Cd2 plus and 2E minus, and nickel 2 plus gets reduced to nickel. So, the final reaction, total reaction is Ni2 plus cadmium gives Ni plus Cd2 plus. So, that is the overall reaction. So, the corresponding voltages are given by the cell potential with respect to hydrogen. So, V naught Ni minus V naught Cd. So, here comes the reduction. So, reduction potential minus oxidizing potential. So, reduction potential is minus 0.25, oxidation potential is 0.403, right, and so you get 0.153 volts as the voltage from the cell. So, plus 0.153 volts is coming from this cell. Now, it is important to understand that this plus and minus reaction signs indicate whether the direction of reaction is correct or not. Of course, since we know that for standard electrode, which is going to be the cathode and which is going to be an anode based on its position in the EMF series, there is no question of going wrong here, because you have you will always get a positive sign if you are using the electrochemical series correctly. But if you do get a negative sign over here, it means that there is some mistake in using the electromotive force series, EMF series, and one has to check the relative positions and the corresponding reactions which have been, or basically the voltages taken here. So, basically what it means is that if you have assumed that the nickel is going to oxidize and cadmium is going to reduce, for example, then you will get a negative value over here, and then it will indicate that the positions of cathode and anode are the other way around, right? Because otherwise what will happen is, supposing you take nickel to be oxidizing and cadmium to be reducing, then it will be minus 0.03 minus 0.250, and it will give you minus 0.153 volts, and that minus sign will indicate that the positions of the oxidation and reduction have to be interchanged, meaning the assumption that cadmium gets reduced and nickel gets oxidized is wrong. So cadmium has to get oxidized and nickel should get reduced, and that is precisely what will be the conclusion from the EMF series. So one can detect errors in deciding on cathode and anode based on the sign of the delta V. Now when the electrochemical concentrations change, so for example you have a non-standard molar concentration and also non-standard temperature, then half cell solution is with 1M is no longer available, because these voltages pertain to a hydrogen electrode and specific concentration and specific temperature. Now in this case temperature is 25 degrees centigrade, so temperature is not much of an issue, but then concentration is. So one has to make a initial guess, some sort of educated guess as to which metal species is will get oxidized and which will get reduced. And when delta V, as I was explaining earlier, when delta V acquires a positive sign, then the choice is right. If delta V acquires a negative sign, it means that the educated guess which we had made was wrong. So if we see this, let us assume that cadmium 2 plus nickel gets, so cadmium 2 plus gets reduced to cadmium and nickel gets oxidized to Ni2 plus. So that is what is the assumption under non-standard conditions. Under standard conditions, this assumption is obviously wrong, because of the fact that you have nickel higher in the EMF series as compared to cadmium, but in a non-standard condition you have a non-standard assumption which is not based on the EMF series, contrary to EMF series, and we need to find out whether we are right in assuming something else. So now we continue our solution here. So you have V naught CD, so this is now the reducing voltage. You see that so now this is reduction and this is oxidization. So here also we had taken here Ni was getting reduced and cadmium was getting oxidized. So here you get cadmium getting, so instead of nickel it is cadmium getting reduced and nickel getting oxidized. So that is why we have cadmium getting reduced, V naught CD minus V naught nickel minus RT NF. R is the gas constant, T is the temperature in Kelvin, N is the number of valence electrons, which is 2 in this case, zinc has 2 plus valency, and F is the Faraday's constant. And then we have the molar concentrations of Ni2 plus and cadmium 2 plus. Again Ni is getting oxidized here and cadmium is getting reduced here. So here we have Ni2 plus upon Cd2 plus. So Ni2 plus is 10 to the power minus 3 and this is 0.5 molar concentrations. Now since the temperature is as per the standard temperature of 298 degrees Kelvin, right, T is 25 degrees centigrade, 298 degrees Kelvin, R is the gas constant, and so all this taken together gives us this value, it gives us this value. Actually RT upon Faraday's constant will give us 0.0592. Now this is ln of Ni2 plus upon Cd2 plus, and this is log to the base 10. So this factor also includes the factor of 2.303 to convert ln into log to the base 10. So, that is also taken into account over here. So, now what we get is minus 0.403 volts minus 0.250 volts of nickel, and then minus this fraction, which gives us minus 0.073 volts. So, again this minus 0.073 volts means there is a small voltage, but the direction of oxidation and reduction which we had assumed is not right, it has to be changed. So, when delta V is negative, the spontaneous reaction direction is opposite to that of our earlier guess, that nickel gets oxidized and cadmium gets reduced. So, we therefore infer that the cadmium has to get oxidized and nickel has to get reduced to generate 0.073 volts, and so the reaction therefore still proceeds as before, Ni2 plus Cd giving Ni plus Cd2 plus, right. Now, with the temperature changes, let us say the temperature changes, then if it changes to let us say 50 degrees centigrade, then we have delta V equal to minus 0.0665 volts. So, there is instead of 0.073 minus 0.073, we have 0.0665 volts. So, basically the situation of this kind remains unchanged, because again there is a negative sign. So, if we assume this to be the case, okay, if we assume this to be the case, that is not so, and therefore in reality it is Ni2 plus becoming Ni and cadmium becoming cadmium 2 plus. So, if you change the molar concentration from 10 to the power minus 3 to 10 to the power minus 5 for nickel, let us say you make the nickel concentration much thinner, okay, and then we make cadmium concentration from 0.5 to 1.5 molar. So, 10 to the power minus 5 moles for nickel and 1.5 moles for cadmium, it leads to a negligibly small voltage of minus 4.77 into 10 to the power minus 5 volts. So, practically you get a 0 voltage. So, you see that there is a transition from the previous voltage. So, a change in the molar concentration and temperature would lead to a transition from 0.153 volts to 4.77 into 10 to the power minus 5 volts with a change in molar concentration and change in temperature as well. So, basically this is just to show that a time may come when this sign will turn out to be positive. So, as the molar concentrations change, well, there is a limit to change in temperature, because if temperature goes beyond 100 or so, the whole thing will start boiling. So, if it starts boiling, then of course I mean you cannot exceed that temperature, because the water will get lost and the molar concentrations will keep on changing as water gets removed from the solution. So, so what it means is that the temperature changes are relatively limited, but molar concentration changes can occur. Well, if the temperature goes too high beyond the boiling point, then molar concentrations will also change as a result of water being lost. Okay. Now, we come to another problem. For each of the metals listed in the following table, magnesium, vanadium and zinc, you have been given the density of the metal, you have been given the formula for the metal oxide, and you have been given the density of oxygen. Now, this is about finding out whether the oxidation will take place so as to protect the material, or the oxide will fail to protect the material from further oxidation, right. So, we are going to see what is called as the Pilling Bedworth ratio, which decides whether the oxide is going to be tenacious, whether it is going to protect the material, or whether it is going to spall off and cause further oxidation, or is it going to be porous, for example, right. So, on the basis of this value, we have to specify whether this value means Pilling Bedworth ratio value. We have to specify whether you would expect the oxide scale that forms on the surface to be protective, and then justify your decision. So, density has been given over here, and one thing is to be understood that a high degree of adhesion between oxide film and metal, comparable coefficient of thermal expansion for metal and oxide, and for a relatively high melting point and good high temperature plasticity, all are required for a protective oxide. So, if the oxide film is to be protective, then there has to be high degree of interfacial strength between the oxide and the metal, the comparable coefficient of thermal expansion. So, if the thermal expansion of one let us say substrate and the oxide are very different, then it will generate tensile stresses in the oxide, which can result in fracturing of the oxide. Similarly, if again the difference is very large, the oxide might get compressed too much, and therefore again it will result in spalling off of the oxide. So, the thermal expansion has to be different, has to be the similar, not different. For the oxide, the relatively high melting point should be present, and a good high temperature plasticity is also important, because if you are working at high temperatures where oxidation is much more severe, oxide should also be able to deform with the substrate. If the oxide does not deform with the substrate, it becomes brittle, then it is going to just fall off, it will just get knocked off from its position and expose further metal for oxidation. So, a high melting point of oxide and high temperature plasticity becomes very important. Typically, protective oxides have a Pilling Bedworth ratio between 1 and 2. So, if the Pilling Bedworth ratio is less than 1, it means that the A oxide, atomic weight of oxide into density of metal divided by A metal, atomic weight of metal divided by density of oxide. So, if this ratio is less, then it means oxide is going to be porous in nature, right. Oxide is going to be more porous, because the density of the oxide, so AO, A naught is more. So, basically what it means is that the atomic weight of oxide is far too high as compared to metal, and so it is going to be much more porous. And if the ratio is more than 2, if the ratio is exceeds 2, then it means that it is a non-protecting oxide, because it can spall off very easily. And so, that is the reason why we need to see how the oxide will protect or not protect. So, here I have taken the same 3 metals, magnesium, vanadium and zinc, and then I have added 3 more oxides of iron, which are very commonly found. The principles remain the same, but then for sake of comparison, for sake of understanding, I have added 3 more oxides. So, one is FeO, Fe2O3 and Fe3O4. Now, these oxides, these 3 different oxides form under different conditions of availability of oxygen. For example, FeO would be formed when the oxygen is relatively less available. So, small quantity of oxygen is available, that is because you have 1 atom of oxygen per atom of iron. Fe2O3 has got the maximum 1.5 atoms of oxygen per atom of iron, and here you have Fe3O4 where 1.33 atoms of oxygen per atom of iron are available. So, if copious quantities of oxygen is available, you form Fe2O3 and Fe3O4. On the other hand, if the oxygen is relatively less, then you tend to form FeO, and these densities of these different oxides are given over here. So, for instance, magnesium oxide has a density of 3.58 gram per cc, 3.36 is for vanadium, and zinc is 5.61. Now, if you look at the relative densities between the metal and that of the oxide, you see that density of metal 1.74 and oxide has 3.58 grams per cc, right. Oxide has got a higher far higher density, In case of vanadium, it is 6.11 and 3.3, though density of oxide is far lower as compared to density of metal, right. Here zinc 7.13, zinc oxide just 5.61, iron 7.8 gram per cc, here it is 5.74. So, the oxides in case of many of these metals have a density that is far lower than the density of the metal itself. The atomic weight of the metal, each of these individual metals are given here. So, 24. So, these are basically rounded off to the next decimal place. So, usually you will have the atomic weight 23 point something or 24 point something or 50 point something, 51 point something and so on. So, here it is 55 point something, which has been rounded off to 56. So, now here you have the atomic weight of oxide. This atomic weight of oxide has to be found as per the formula. So, MgO, so you have got atomic weight of metal 24 plus atomic weight of oxygen is 16 grams per mole, and therefore, you get atomic weight of the oxide as 40. Similarly, V2O5 vanadium pentoxide. So, 2 atoms of vanadium 51 into 2 plus 16 into 5, that is 80, that gives us 182 as the atomic weight of vanadium pentoxide, right. Similarly, we have for zinc 81, for FeO you have 72. So, zinc oxide has 81, FeO has 72, Fe2O3 160, Fe3O4 232. So, now if we calculate the Pilling and Bedworth ratio for magnesium oxide, so you have A0 rho m. So, you have atomic weight of oxide into density of metal into 1.74 divided by Am upon rho naught. Am is atomic weight of metal 24, and rho O is the density of the oxide. So, 3.58. Rho O is not 0, it is O. So, rho O is the density of the oxide. So, 3.58. So, here the density is smaller, but so rho 0 is greater. Okay, rho 0 is greater, it is a denser oxide, and therefore, you get the Pb ratio which is less than 1. Less than 1 means the oxide is porous. Okay, the oxide is porous, it is not able to therefore. So, ideal ratio is 1. I mean, there is no change at all. If A0 rho m upon Am rho naught is AO rho m divided by Am rho O is equal to 1, that is the most ideal situation where there is absolutely no change in volume. But now in this case, the volume of overall oxide is volume is less, so it is porous, and so it is unable to protect the base metal from further oxidation. If you take vanadium, it is the other way around. The volume is so large that it will just get removed, it will just spoil off, it will not adhere to the surface, because what happens is the adhesion and so the thermal expansion etc. Will be much more for the oxide. I mean, already the volume changes are very significant, the volume of oxide is very high, and therefore, it will tend to spoil off. Comparatively, zinc, if you take zinc, it is 1.58 and similarly FeO is between 1 to 2. So, here you will get a protective oxide film, So, comparatively Fe2O3, which is called as rust. So, rust actually does not protect the iron from getting oxidized. So, the reason is that the Pilling Bedworth ratio is more than 2. Here also the Fe3O4 Pilling Bedworth ratio is more than 2.08. So, these oxides, namely vanadium pentoxide, Fe2O3, Fe3O4 do not result in protective oxides, whereas here you have a good amount of protection being given. So, in fact, if there is a process called as bluing, that is this oxide FeO appears blue. So, if you give this treatment to, let us say, tool steel, it makes a relatively wear resistant oxide on the surface which is adherent to the surface, and which also increases the frictional I mean it also increases the life of the tool by decreasing the frictional coefficient between the workpiece and the tool. So, many tools are given this treatment. So, this oxide is a protective oxide, right. Yeah. So, and then the final problem is about weight gain, again about oxidation, but then we see the weight gain. There are three different rates of oxidation. Again, when we talk about oxidation, rate of oxidation becomes important. One is a linear rate of oxidation, other one is parabolic rate of oxidation, and third one is logarithmic rate. Now, the rate at which the oxides grow also decide whether they are going to be protective or non-protective. Okay. So, you see that if the parabolic rate of oxide growth is observed, then there is an adherent non-porous oxide film that is followed. So, basically we would like a parabolic rate of reaction. However, if it is linear, okay, if it is linear, then it is a non-protective film that is porous, or it falls off, exposing fresh metallic surfaces to oxidation. So, we would not like to have a linear rate of oxidation, and a parabolic rate of oxidation. So, weight gain with respect to time. Weight gain is because of oxide getting into the metal, formation of oxide, right. And the layer growth is due to ionic diffusion through an oxide film. So, basically the growth of the oxide is governed by the diffusion of ions through the oxide film, and that is protecting. So, now if you take this, one has to find out whether this weight gain corresponds to a protective oxide film or non-protective oxide film, right. You have measured the weight gain, and you need to find out whether it is desirable or not desirable. So, now if you look at the various constants, we have I mean, after fitting a curve r square equal to 1, we get these this linear fit, and it looks like it is mildly parabolic in nature, where the parabolic constant is small, but then for r square equal to 1, it you have a parabolic relationship fitting this. And so, given these constants, you can estimate that at 600 minutes the weight gain will be 40.89. So, 40.9, roughly 41 milligram per square centimeter. So, basically this is how you can find out whether the oxide is going, how protective that oxide is going to be. So, if it is more parabolic in nature, meaning the square term has a higher coefficient, then you will find that it is even more protecting. So, thank you very much. So, this is all about the numerical problems pertaining to corrosion.